Alors aujourd'hui, dans le séminaire consacré à la représentation des objets mathématiques et de l'intuition mathématique dans le cerveau et dans les machines, je vous avais dit qu'on essaierait d'alterner entre des représentants de l'intelligence artificielle et des personnes qui analysent expérimentalement comment les objets mathématiques sont représentés dans la pensée et dans le cerveau humain. And today I switch to English. I am extremely happy to welcome one of the most prominent representatives of research on the representation of mathematics and especially numbers in the human brain and the human mind. This is Professor Daniel Ansari. Professor Ansari came all the way from Canada, from London, Ontario, to be with us today and yesterday as well. We worked on education. Professor Ansari is actually appointed jointly by the Department of Psychology and by the Faculty of Education in the University of London, Ontario, and is creating paradigms and doing research which is at the boundary indeed of cognition and education, trying to understand not just how adults represent numbers, but especially how we come to learn arithmetic, and eventually, and this is a topic that we talked about on Wednesday when we had this launching of the initiative Agir pour l'éducation au Collège de France. Vous avez peut-être entendu parler que le Collège de France lance une grande initiative sur l'éducation. We want to understand how we can use cognitive science to facilitate the process of education, to facilitate the changes that must occur when you understand number and when you get more fluent in numbers. There are many interesting problems. How do you understand, let's say, negative numbers? How do you understand fractions? How do you understand, why not, complex numbers, which were called imaginary, because for decades, even the top mathematicians could not understand, how you work with these objects. So this process has to restart in the brain of every child as they go to school and try to figure out what we mean by numbers and by arithmetic. So this is the topic of the presentation today, number symbols in the brain and mind. Thank you very much, Daniel, for coming all the way to talk to us today.
Thank you very much, Stan, for that kind introduction. It's great to be here and to have the opportunity to share some of our work. So I just want to start with a broad introduction to the field of numerical cognition and why it's relevant. I think we can all agree that numbers play a fundamental role in our everyday lives. For most of you this morning, you would have gotten up and probably looked at your alarm clock, or nowadays most of us look at our phone. And we use numbers to guide our actions. If I'd seen this number on my alarm clock in my hotel nearby here, I would have been in a sheer state of panic because I knew I would have missed this lecture. You might then turn to your favorite news website and look at the latest business information if you're so inclined. And that, again, those pieces of numerical information will guide your thoughts as well as your decision making. You may go on a trip and you need important numerical information to guide your actions and your thinking in those contexts, such as your gate information, your flight departure, and so forth. And we know that when we make numerical mistakes, the consequences can be very costly. So miscalculations have their price in our everyday lives, or in even more dramatic situations, such as this engineering accident here. Well, beyond sort of the everyday context of how important numbers are, what do we know about the importance of numerical skills more generally speaking? We know that low numeracy is associated with lots of adverse outcomes such as unemployment, physical illness, depression, and even incarceration. Of course, these are just associations, these are correlations. It doesn't mean that low numeracy causes unemployment. However, it is a contributing factor that we need to take into account and pay attention to. We also know from data from the OECD, based here in Paris, of course, that improvements in mathematical competence as measured by the Program for International Student Assessment, or the PISA test, are predictive of measures such as economic growth. So we know there's a tight link between the quality of a country's mathematics education and economic measures such as changes in its GDP over time. And then perhaps domains that we think less about, numbers also play an important role, such as in healthcare. You can imagine a busy nurse on the floor of an emergency room on a busy Friday night, reading off numbers of one instrument, using those numbers to guide that individual's actions. If there is any kind of mistake being made, that's going to be costly for the patient. Or on the patient side, you can imagine a patient with low numeracy abilities having trouble adhering to certain prescription regimens and so forth. And that's led to actually the creation of a domain called health numeracy, where people actively study the relationship between numerical competence, decision-making, and healthcare-related consequences. So this is just to sort of illustrate that numbers really play a broad role in all aspects of our everyday lives. And therefore we need to better understand how children develop numerical skills so that we can best understand the developmental pathways that they take and where things may go awry so that we can intervene using evidence-based methodologies. Which then leads me on to the next question, which is how actually do numerical skills develop? And it's fair to say that over the last 30 years or so, developmental psychologists, cognitive neuroscientists, and cognitive scientists have made tremendous progress, not only in understanding how children learn to read, but we've now gone to the next level where this knowledge is being actively translated into classrooms and having a great impact. When it comes to the development of numeracy skills, we're lagging behind. There's less research on how children develop numerical skills compared to how children develop literacy skills. However, the research is catching up and will soon, I think, start to also see the same sort of impact on the classroom as well. So when we think about how children develop numerical skills, a good way to start is by looking at what we might refer to as foundational skills. So if you think about foundational skills, a good analogy might be to that of phonological awareness in the domain of reading. We know that children's awareness of sounds in their language is predictive of their later reading skills and their ability to connect speech sounds to letters, which is called decoding or phonics. Now, in the domain of mathematics, we know slightly less about those foundational skills, but let me try and take you through some of what we know. Why are foundational skills so important? Well, we know from, again, research on reading that those children who have good foundational skills undergo a trajectory of steep growth. So you can see here, if I can find the pointer. Yes. You can see that those children who have good foundational skills undergo this great trajectory of growth in terms of their reading achievement, and they become skilled readers. But those kids who lack those foundational skills early in development undergo a shallow trajectory whereby they don't show much growth in the early years. So foundational skills are really critical at giving children the necessary scaffold to be successful when it comes to reading, and the same must be true when it comes to mathematics as well. So what do we know about the foundational skills underlying math? Well, there's been a lot of effort devoted to understanding how we and other species process sets in the world around us. And we refer to those as non-symbolic representations of number. You can look at this swatch of dots and quickly make an estimate of how many dots there are. You can also compare it to another set of objects and decide which one is larger or which one is smaller. So we have very good basic intuitions around quantities without needing to use symbols to represent them. And fascinatingly, we know from a long line of research in infancy developmental psychology that even very young infants and babies can discriminate between dot arrays. So for example, in a seminal experiment, Fei Xu and Liz Spelke showed that 6-month-old infants can discriminate between 8 and 16 dots, but at the same time, these infants can't discriminate between 8 and 12 dots. So they have some rudimentary intuitions around numerical quantities, sometimes referred to as an approximate number system. We also know from comparative research that non-human primates are very capable of processing non-symbolic numerosity. So for example, non-human primates can discriminate which of 2 dot arrays is numerically larger. And again, they have this fuzzy representation of numerical magnitude, whereby they are better at discriminating dot arrays that are quite far apart in terms of their numerical value compared to pairs of non-symbolic numerosities that are relatively close together. And finally, we also know a lot about the neural correlates of these basic numerical intuitions. So we know that areas in and around the interparietal sulcus are sensitive to, for example, the change in the number of items in a set, or that these areas are activated when we engage in comparison of set sizes, when we're, for example, presented with different sized dot arrays and have to decide which one is numerically larger. And beyond sort of the coarse level of human non-invasive neuroimaging, we know that there are single neurons within the interparietal sulcus that are tuned to specific numerosities in an approximate way. So we have a very good sense of the sort of biological foundations of our numerical understanding. And we know that there's a lot of continuity over developmental time in these systems as well. So this is beautifully illustrated in this figure from a review paper by Melissa Libertus and Brannan, where you can see sort of a summary of the state of the art, whereby you see that the brain, particularly the interparietal sulcus, responds to changes in non-symbolic numerosities, both in very young babies. This is data from Veronique Guizard's work using EEG source localization. You can see here in the right interparietal sulcus responds to a change in the number of dots in the brains of very young babies. And then work by Cantillon and Brannan showing that in 4-year-old children you see a very similar brain region, again in the right hemisphere, being responsive to changes in numerosity. And then finally work by Manuela Piazza showing the same. So we can see that over ontogeny, over the course of human development, these brain systems don't seem to change very much. Of course, when it comes to human children, we're not just dealing with individuals who discriminate between set sizes, but in cultures in which there are formal education systems, children have to learn symbolic representations of number. And symbolic representations of number are a relatively recent human cultural invention. They've been around for about 6,000 years, and they've changed dramatically over the course of human cultural evolution in how we represent symbols, in how we represent quantities symbolically, starting out with very iconic representations, such as these hatch marks, to the completely non-iconic Hindu-Arabic numerals, which have now become an almost universal language of mathematics around the world. So this raises the interesting question of how the innate and acquired systems are related to one another. How are the basic intuitions that we share with other species that seem to develop very early related to the invented cultural systems for the representations of numerical quantity? And in this way, the domain of numerical cognition is a really interesting way to explore the interactions between culture and biology over the course of human development. To what extent do biologically primary systems, such as the approximate number system that supports non-symbolic number processing, scaffold the acquisition of cultural systems such as the Hindu-Arabic numerals, or is there some bidirectionality between these two systems? It is this question that I want to devote the next part of my talk to, where I want to explore how the non-symbolic innate systems are related to symbolic cultural representations of numerical quantity. And of course, there are 3 different possibilities here. Perhaps the most intuitive possibility is that the capacities that we're born with, that we can already detect very early in infancy, that we share with other species, scaffold our acquisition of symbolic cultural representations. But of course, when we deal with two systems and the relationships between them, we also need to consider that the reverse may be true. That when children learn symbolic representations of number, that changes the way in which they process sets in the world around them. Or indeed, it's entirely possible that the relationships between our non-symbolic innate representations of number and our symbolic cultural representations of number are related to one another bidirectionally and are completely intertwined over developmental time. So how do we go about probing these kinds of developmental dynamics? Well, what we need is longitudinal data. What I mean by longitudinal data is repeated measures of children's ability to interact with symbolic and non-symbolic numbers over developmental time. And if we have those repeated measures, then we can begin to estimate developmental relationships. So we can ask questions such as, do individual differences in non-symbolic number processing early in development scaffold the acquisition of symbolic number abilities or vice versa? So the first study that I want to describe to you is one that was run by Ian Lyons, who was a postdoctoral fellow in my lab, who's now at Georgetown University in Washington, D.C. And we had the opportunity, in collaboration with the Toronto District School Board, which is North America's largest and most diverse school board, to collect data from 35 schools in Toronto. The children were at that time in what we refer to as senior kindergarten. Canada, or Ontario at least, has 2 years of kindergarten, junior and senior kindergarten. In senior kindergarten is the year just before children enter elementary school. They're around 5 years of age, between 5 and 6 years of age. And we had the opportunity to test them both in the fall of their senior kindergarten year, so just when they began senior kindergarten, and closely towards the end of their senior kindergarten year, so sort of spanning that senior kindergarten year. And we had paper and pencil measures. For brevity today, I'm just going to be talking about two of them, which are our non-symbolic measure of number processing, this dot comparison task. So children see this on a page and have to cross out the numerically larger of the two dot arrays or the numerically larger of the two symbols as quickly and as accurately as they can. And they're given 2 minutes per test. So this is a rather rapid kind of instrument to get some insights into their symbolic and non-symbolic number processing abilities. So how did we go about analyzing this data to find out something about the relationship between our innate representations of number and our more cultural symbolic representations of number? Well, in this particular analysis, what we looked at was the relationship between beginning of kindergarten and end of kindergarten using a multiple regression model. So what we do here is we take their non-symbolic performance at time 1, so when they've just entered kindergarten, controlling for the correlation between symbolic and non-symbolic at time 1, so that then we can estimate how much non-symbolic at time 1 contributes to the change in symbolic number processing. Then we also estimate the reverse direction, where we now look at whether individual differences in symbolic number abilities at time 1 predict change in non-symbolic number abilities. So again, we control for the autoregressive effect of non-symbolic at time 1, and then predict non-symbolic at time 2. So what did we find? Well, perhaps counterintuitively, what we found was that the direction from non-symbolic to symbolic was non-significant. And in turn, the direction from symbolic to non-symbolic was highly significant. So this then suggests that at least at this age, at age 5, it is not as though the approximate number system is scaffolding changes in symbolic number processing, but rather the reverse is true, that the acquisition of symbolic number influences the development of the non-symbolic number system. So that's the conclusion from this first study. However, there were several limitations to this study, and we wanted to carry out a follow-up study in which we added an additional time point. So this is the same children, but now we have an additional time point at the end of grade 1. And in addition to symbolic and non-symbolic number comparison, we also had another task here, which is what we call mixed comparison, where now you have to sort of perform an integration of the two representations by comparing which one of these two is numerically larger. It turns out that this is actually quite a difficult task. And we also had some simple mental arithmetic to get an idea of the children's rudimentary arithmetic abilities. Now, in this particular study, we used what is called a random intercept cross-lagged model. This is an innovation in regression models and structural equation modeling, where you can better distinguish between within subject versus between subject change over developmental time. So in traditional regression models like the one I showed you before, we can't make that distinction. Here we can, what we really want to do is understand within person change rather than between person change over developmental time. So in this kind of approach, what you do is you formulate several different models for what the developmental dynamics might look like, and then you test which of these models best fits your data. So in this particular case, we tested 3 models. The first one was the mapping model. So we've got our 3 time points here, beginning of senior kindergarten, end of senior kindergarten, middle of grade 1. And we've got our different measures. And in this particular model, we're testing whether non-symbolic at time 1 basically predicts everything else, whether it is the driver of developmental change in the other competencies in both the mapping or the mixing, if you like, as well as the standard symbolic number comparison, as well as mental arithmetic. Now we contrast that to the refinement model, where now it's symbolic that drives developmental changes. And then finally, we also include a fully bidirectional model, where essentially everything is related to everything else. And what we found was consistent with our earlier data, now controlling for the differences between within and between subjects changes, is that the mapping model best fit the data. So once again here we have evidence to suggest that it's symbolic that drives changes, not only in non-symbolic number comparison, but also in the ability to map between number symbols and dot arrays, between these symbolic and non-symbolic representations, and that eventually influences also the grade 1 grades. We now also have standardized province-wide testing data from a measure called the EQAO, which is a standardized measure administered to all students in grade 3, and we see very positive correlations again between symbolic number development and these later standardized math grades. However, you may say, well, you tested children when they were 5 years of age. A lot of development has already happened by age 5. So can you really make a claim about symbolic driving non-symbolic when it's possible that early in development, it's non-symbolic that drives symbolic, and then symbolic goes on to shape non-symbolic? It is possible to have this kind of developmental dynamic as well, and you can only tell that by testing significantly younger children, children who haven't had much exposure to symbolic number yet, who are very much in the early phases of getting their numerical abilities off the ground. Well, just a couple of months ago, Dan Hyde's group from UIUC published a paper that actually directly addresses this question. So I just want to share some of the key results with you. So what they did in this paper is they tested significantly younger children. So these are children who are between just under 3 and just over 4 years of age. They were tested in a 1-year longitudinal study with 3 time points, right at the beginning, then 2 weeks later, and then almost a year later. And they were tested on verbal number knowledge, so things such as, can you, for example, if I ask you to give me 5 objects, can you give me 5 objects? And if you can do that, that means you have a representation of 5. You understand how the number word 5 relates to the real word quantity of 5, something sometimes referred to as the cardinality principle. They also measured general cognitive abilities just to control for general developmental changes, as well as dot comparison to measure sort of the precision of the approximate number system. This now is in much younger children, so we could expect that the developmental dynamics are different. However, what Mu and colleagues found was that indeed, even in these young children, they found that verbal number knowledge drives changes in ANS precision and not the other way around. So again, we've got evidence for unidirectional relationships whereby children's early verbal number knowledge influences how their ANS precision develops over time. And interestingly, they also did an analysis where they included only children who had only very rudimentary verbal number knowledge, and they still found this directionality and not this directionality. So this is just for the 2-week gap here, but they replicated the exact same thing when they look now over the almost 1-year gap. Again, you can see that it's verbal knowledge that drives ANS precision and is also related to math ability, but ANS precision does not predict math abilities. So this is, I think, quite convincing evidence that from the very early stages of symbolic number acquisition, symbolic number changes the way in which non-symbolic representations of number are processed. So the way one might think about this is to think about symbolic number knowledge working as a sort of attentional filter. And in work by Manuela Piazza and colleagues and Professor Dehaene as well, it's been shown that the developmental changes that occur in non-symbolic number processing are less changes in representational precision and more changes in the ability of developing minds to extract numerosity, to extract the total number of items in a set from sets in the environment and to ignore correlated variables such as density, area, contour length, and so forth. So what we think is that symbolic number may play an important mediating role in this process, that symbolic number sort of changes the perception of and focus on non-symbolic sets. Now that you have these precise representations, you start to view the world and sets in the world around you in, to a greater extent in numerical terms, and that allows you then to sort of inhibit distracting variables such as area and density of sets. Now, we've just submitted a grant to hopefully test these hypotheses developmentally and thereby to further understand the mechanisms by which changes in symbolic number drive changes in non-symbolic number rather than the other way around. Now, I want to encourage you now to participate in a very brief experiment with me. I don't have any consent form, so this is completely voluntary. What I will do is I will show you some dot arrays. They will flash up relatively quickly on the screen. And I just want you to say as quickly how many dots you see. And you can shout this out or say it silently. It's mainly about your experience with this. Okay, so here we go. What did you notice? Does anybody want to describe what they noticed about these different dot arrays?
Some are ordered and some are not.
Some are ordered and some are not, okay. Any ones that were particularly hard or any ones that were particularly easy? Yes? Excellent. Very good. Yeah, so hopefully what you experience as you try to estimate the total number of dots that were shown in each of these slides is that there is a dramatic difference between being able to name small set sizes and being able to name large set sizes. So this is a piece of evidence here from Stanislas Dehaene's lab, Susanna Refkin's paper, where participants were asked to name 1 to 8 quantities, and what you can see here is this, what we in Canada refer to as a hockey stick function, where you've got a very shallow increase in errors, almost no increase in errors from 1 to 4, and then this dramatic increase in errors. And the same is true for reaction time and also for the variation in your responses. So people are very, very accurate. Don't really name any other numbers for 2, 3, and 4, but as soon as you get to larger numbers, there's greater variability in which numbers are estimated. So this is a classic psychological finding, and it's been suggested against the background of data such as the ones I've just shown you, that there are two distinct systems for non-symbolic number processing. One which we call the approximate number system, which underpins our ability to process large numbers approximately and to perform estimations, and the other one called subitizing or object file system, which allows us to enumerate small arrays of objects very quickly and very accurately. Now, in the context of thinking about the relationship between symbolic and non-symbolic number, given that there are two different systems for non-symbolic number processing, we might posit that the developmental dynamics between symbolic and non-symbolic number differ as a function of set size. So we already know from the data that I showed you in the first part of my talk that when it comes to large numerosities, the direction is very much from symbolic to non-symbolic. But what about when it comes to small sets, to subitizable sets, to sets which we can very accurately enumerate very quickly? Are the developmental dynamics different? Is it perhaps here that we see that non-symbolic drives symbolic, or is it the same that symbolic drives non-symbolic, or are the relationships bidirectional? Now, in order to address this question, Jane Hutchison, who was an undergraduate student, then RA in my lab, and then went to do her PhD with Ian Lyons at Georgetown University, addressed this question by testing 540 children. These were also from the Toronto District School Board project. They were between 4 and 6 years of age, were tested in the fall and spring of kindergarten. And what Jane looked at was the relationship between symbolic and non-symbolic separately for small, so in this case it's numbers and numerosities never exceeding the subitizing limit of 4, or large. So are there different developmental dynamics in the small number range between symbolic and non-symbolic compared to the large number range between symbolic and non-symbolic? So let's look at the cross-sectional results first for both the fall and the spring. So this is just looking at the raw correlation between symbolic and non-symbolic. And what you can see very nicely here is that both in the fall as well as in the spring, the relationship between symbolic and non-symbolic is greater for small than it is for large, and that's very consistent. But what about the developmental dynamics? What about the relationships over developmental time between symbolic and non-symbolic for small and large separately? What we see here is something quite interesting and different from the data I showed you before. For small, we see clear evidence for a bidirectional relationship. It's slightly asymmetric in that the relationship from symbolic to non-symbolic is stronger than from non-symbolic to symbolic. But for large, consistent with the previous data I showed you, we see very clear evidence for a unidirectional relationship. So this then suggests that there's a differential developmental dynamics, whereby for large we see that symbolic number development shapes the approximate number system that underpins large number processing. But for small numbers within the subitizing range, the relationship is bidirectional. And I think this is interesting from the point of view of how children get symbolic numbers off the ground and what roles might be played by exact enumeration and the ability to very rapidly and exactly enumerate small sets. And I think more work needs to be done in this area to better understand these developmental dynamics and their implications, as well as their earlier developmental origins, because again, in this paper, we're looking at 5-year-old children. I now want to switch a little bit to how we can translate this kind of work, this kind of thinking around foundational competencies to education. And one way in which we've been doing that is by designing instruments for screening young children and making them available for free to educators and parents. One of these tools that we have designed and put online, you can check out this test at www.numeracyscreener.org, is a very cheap and quick paper and pencil test of symbolic and non-symbolic number comparison. So this should be familiar to you by now. Children are asked to cross out the larger of the two dot arrays or the larger of the two Arabic numerals as quickly and as accurately as they can. And using this measure, we've been able to ask research questions, but also more applied questions. So one of the questions we early on wanted to understand was, of course, does this instrument have any kind of validity? In other words, does this instrument predict math scores over time? And we ran a number of studies. I'm just sharing one here by Zach Hawes, former PhD student who's now at the University of Toronto, who in just close to 400 kindergarten children showed that individual differences in both the symbolic version of the test and the non-symbolic version of the test predict mathematics grades in grade 1. And we now also have the standardized measure and see much the same relationship. But interestingly, and this is a point to bear in mind for data that I'm going to present afterwards, we found in many different studies that when we directly sort of contrasted the contributions of symbolic and non-symbolic to things such as math grades, that symbolic explained unique variance in individual differences in math grades, but non-symbolic did not. And that's controlling for a variety of factors, such as the children's age, their gender, some information about their language abilities, their arithmetic, as well as their number line, estimation performance. Symbolic comparison always comes out on top, at least in these samples, in these Canadian samples. Now, as I've said, we've tried to really work with educators to see to what extent we can design measures that will really help them in their everyday practice. And one example of this is a collaboration we engaged in with members of the Halton District School Board, which is near Toronto. And we not only administered our numeracy screener, but also engaged teachers in reflections around how useful they find this particular tool. And what you can see here is the results are relatively positive, but we still have work to do. So over half of teachers in this particular school board thought that the numeracy screener is either very useful or extremely useful, but you also see a proportion of educators who think it's only slightly useful. So there's still more work to be done with this particular tool. But it's been really interesting in sort of directly working with educators and those involved in research and assessment divisions within education. So this first author here is actually the director of the research and assessment division of the Halton Catholic District School Board. And I think these kinds of collaborations are really important in order to bring research to the classroom. Now, one of the main reasons why Nadia Nosworthy and I designed the numeracy screener in the first place is that we wanted a measure that we could use in a variety of different contexts. And we've now collected data in many different contexts. Here you see, for example, an outdoor school in India, a school in Ghana, and we have now got data on the numeracy screener from 6 different continents, 13 countries, 16 regions, and 18 data sets. And we're about to start sort of a meta-analysis of this data to try and understand sort of the consistent patterns as well as the cross-national differences in children's performance. All of this data is from children in kindergarten or grade 1. But I want to present you with some data that has left us puzzled. And we're still sort of trying to figure out what it means. But it's data that we collected in Ghana and data that we collected in the Ivory Coast. And this was enabled through a collaboration with Sharon Wolf, who's at University of Pennsylvania in the United States. And Sharon was able to collect data as part of a larger project from almost 400 children in Ghana who were between 7 and 9 years of age. And as well as collecting data on the numeracy screener, which is this test of symbolic and non-symbolic number comparison, we also collected their early grade math assessments. The EGMA is a standardized test of early math abilities that is quite often used in low-income countries. And when we first looked at the data, everything looked really good. This is just looking at the early grade math assessment and the numeracy screener total score, so across symbolic and non-symbolic. You see a nice positive correlation whereby students who perform better on the numeracy screener also perform better on the EGMA test. But then we found something that really puzzled us because it was completely contrary to the data we were seeing in our Canadian samples. And what we found here was that there was quite an impressive correlation between non-symbolic comparison and the EGMA. And not only that, it was significantly stronger than the correlation between symbolic comparison and the EGMA. So this is directly the opposite of what Zach Hawes, for example, found in our data from the Toronto District School Board children. And indeed, we went further and conducted a multiple regression in which we can ask, which one of these, symbolic or non-symbolic, or both, is a unique predictor of EGMA scores. And what we found was that non-symbolic came out as a significant predictor of math scores in Ghana, but symbolic did not. And these findings, of course, as I've already said, run counter to those from Western countries. So we were a little bit puzzled, and we were, of course, worried that this was an artifact of the sample. We double-checked everything, so finally, Sharon said, why don't we replicate this in another study that we're running in the Ivory Coast, which is a neighboring country of Ghana, of course. So we pre-registered and went out to collect data in the Ivory Coast. Again, a sample of just over 350 children, similar age range, similar test, numeracy screener, well, identical test, numeracy screener, and the early grade math assessment test. And what did we find here? Well, we found exactly the same pattern. So we found that in children from Ivory Coast, it is non-symbolic number comparison that is a stronger predictor of their EGMA scores than symbolic number comparison. So these data, and then with multiple regression, just like in the data from Ghana, we were able to show that it is indeed non-symbolic but not symbolic that explains unique variance in children's math scores in the Ivory Coast. Now, as I've already said, this really runs counter to everything that's sort of been out in the literature so far. So this is data from a meta-analysis. But in this meta-analysis, there's exclusively Western samples. So exclusively European and North American samples. And what the meta-analytic estimate suggests is that the correlation between symbolic number comparison and math performance is significantly greater than the correlation between non-symbolic number comparison and math performance. Now, of course, our data from Ghana and Ivory Coast are contrary to these data. And I think they really urge us to pay closer attention to the way in which number knowledge is acquired, to the extent to which that shapes the kind of relationships and developmental dynamics that we're able to observe. Now, we currently honestly have no idea what drives the differences in the correlations between our West African samples and our Canadian samples, or indeed the European samples from the more general literature. But we want to now try and understand, how are children acquiring number in these concepts, what's the role of manipulatives, and how can we better take this context into account. And I think generally this has really highlighted to us that there is such a great need in developmental psychology and cognitive neuroscience to go beyond so-called wide educated, industrialized, rich and democratic, or the acronym for weird populations, and to really try to understand developmental dynamics by adopting a global perspective. We hope to get some longitudinal data as well, so that we can really also see to what extent not only is there a greater correlation between non-symbolic and math abilities than non-symbolic and math abilities in West Africa, but to what extent are the developmental dynamics perhaps different, which would be absolutely fascinating to better understand how context plays into this. Now, before I wrap up and conclude, I just want to also look a little bit to the brain and see what insights can we gain from cognitive neuroscience when we consider the relationship between more primitive, innate systems for number processing, such as the approximate number system, and symbolic systems for number processing. Now, when it comes to non-symbolic number in the brain, I already showed these data earlier. We know that even in 4-year-old children, very similar brain areas are activated when you change, for example, from the presentation of 16 dots to the presentation of 8 dots. And these areas are very similar. You can see in purple the children, in green the adults, and then the overlap. In the right hemisphere, there's an area that seems to respond to changes in non-symbolic numbers similarly in 4-year-old children as well as in adults. And then, of course, the data from Veronique Guizard showing us in a very similar area using EEG that this area is sensitive to changes in the number of dots in the display or the number of items in the display. When it comes to symbolic number, interestingly, what we and others have found is that symbolic number processing tends to be left lateralized. This is data from an fMRI adaptation paradigm. I'll share some more details as to these kinds of paradigms showing that these areas are sensitive to symbolic numbers. And we also know that in areas in and around the left interparietal sulcus, the activation in those areas during symbolic number comparison is correlated with individual differences in math achievement. So these left lateralized areas seem to be very important for symbolic number processing, and right lateralized areas seem to be more important for non-symbolic number processing. And indeed, this notion of these hemispheric differences comes out when you run a meta-analysis. So Mariah Sokolowski, who's a PhD student in my lab, is now a postdoc at the University of Toronto, did a meta-analysis as part of her PhD thesis of all the existing fMRI studies that have looked at both symbolic and non-symbolic number processing. And what you can see here is this nice sort of hemispheric difference, whereby if you look at areas that are more modulated by symbolic number processing, you see activation in the left parietal cortex, and then actually more superior parietal for non-symbolic than symbolic in the right hemisphere. So there do seem to be some hemispheric asymmetries when it comes to symbolic and non-symbolic number processing, perhaps suggesting that these systems, at least in the adult brain, are quite segregated from one another. Now, one of the issues with a meta-analysis like this is that you're looking at between subjects data. So you're looking at data from different studies, different formats. So we sort of wanted to do this all within the same brains, if you like, to better understand how symbolic and non-symbolic number, and we also integrated physical size, are processed within participants. So what we developed for this is a paradigm that we refer to as parallel adaptation. And why we call it parallel adaptation will become clear. So this work done collaboratively by Zach and Mariah when they were both students in my lab. And what they came up with is this solution here. So what you do is you first of all adapt the brain to arrays of 4 sixes. Now these are typically in different spatial locations. I just didn't have other stimuli, so I just copied and pasted the same one, but they are in different spatial locations in the actual task. And what you expect, and this is a ubiquitous neurophysiological phenomenon, is when you repeat a particular stimuli, you see decreases in the response of brain regions that are involved in coding these kinds of stimuli and representing these kinds of stimuli. And that what you can do then is, after you've adapted to a particular stimulus, you can change it. So for in this case, for example, we go from 4 sixes to 4 twos. And what we expect is a rebound effect. So we designed a number of deviants that were interspersed into this train of 4 sixes. We had them in 3 different categories. Symbolic deviance is where you change the symbolic number from, let's say, 6 to 7 or 6 to 2, but the total number of items in the set remains the same. Non-symbolic is where you change the total number of items, but you don't change the identity of the Arabic numeral. In physical sizes, you either reduce or increase the physical size. We had 2 distances because what we expect is that a change from 4 sixes to 4 sevens is going to be smaller than a change from 4 sixes to 4 twos, for example. So we expect that distance 1 leads to less of a rebound effect than distance 4. So by contrasting distance 4 and distance 1, we get an idea of the magnitude of the rebound response. And what we found here was interesting and convergent with the meta-analytic data was again a hemispheric difference whereby symbolic distance modulated areas within the left hemisphere, actually close to the angular and supramarginal gyrus, whilst non-symbolic was associated with a rebound response in the right interparietal sulcus and bleeding into the superior parietal lobe, and interestingly overlapping completely with the physical distance effect as well, suggesting that there might be an intermingling of non-numerical and non-symbolic numerical quantity in the right IPS. Then using representational similarity analysis, we could also ask, well, on a multivariate scale, how similar are these representations? We see great dissimilarity between symbolic on the one hand and physical and non-symbolic on the other hand, which are in turn more similarly represented to each other than to symbolic numerical quantity. So within subjects as well, we see, at least in the adult brain, quite a dissociation between symbolic and non-symbolic number processing, suggesting perhaps that the developmental dynamics I described before lead to the shaping of a symbol-specific system that is quite different from the non-symbolic system. And of course, we need longitudinal data to understand how the behavioral dynamics that I described to you play out at the level of the brain. So let me summarize and conclude. What I've shown to you today is that perhaps contrary to what we used to think, it is not such that biologically primary systems for number representations drive changes in symbolic representations, but that the reverse is true. And now we need to better understand the mechanisms by which the cultural systems kind of change, transform the pre-existing non-symbolic systems that develop early infancy that we share with other species. We also see that these developmental dynamics differ as a function of set size, which might give us some clues as to which non-symbolic systems are most important in scaffolding, in grounding symbols, if you like. We see that individual differences in both symbolic and non-symbolic predict math scores, but interestingly, at least our preliminary data suggests that there might be some important contextual and sort of cultural differences, whereby the relationship is strongest for symbolic in Western samples, but the relationship is actually strongest for non-symbolic in West African samples, suggesting that context matters, and that if we want to fully understand how symbols play out in the brain and mind, we need to look beyond the populations that we typically study. So with that, I'd like to thank you very much for your attention. I'd like to thank my team who did all the work and all the generous funding agencies that have supported our work over the years. So thank you very much, and I think we have time for questions.
Thank you very much, Daniel. Very interesting presentation, a lot of new data. I do have a few questions, and then we'll take them from the audience. But one comment I think is very interesting. I love this distinction between African countries that you studied versus Canada. It reminds me that there is a difficulty with these correlation studies, and the difficulty is the amount of variation. Yeah. It's similar to the heritability studies. People don't know about these measures of heritability, how weak it is, because, for instance, heritability studies based on twins conclude that having 5 fingers is not heritable, because we all have 5 fingers, so there is no variation, so there is zero heritability, according to this measure. So I wonder whether something similar is happening here, that you have different amounts of variability in the populations, just out of what people spontaneously do in the culture and the sample that you have. Yeah. And whether that could explain the differences in symbolic versus non-symbolic correlation.
Yeah, I'd love to talk to you more about how one could capture that within those data. Maybe there's a way of estimating that and making that a systematic comparison. Yeah. I think it's entirely possible. We're trying to also figure out just how children in the Ghana and Ivory Coast samples learn about numbers. Because interestingly, on the raw data, they actually do better on the symbolic comparison than on the non-symbolic comparison. But in the correlation, we see this interesting reversal.
So they actually process the digits well?
Yeah, they do,
All right.
yeah.
Because I was wondering also if that could be an explanation, but maybe not. But this is a question about what you mean by symbols.
Right.
Do you just mean Arabic numerals, or could there be other types of symbols that they use to develop their cognition, but would be invisible in your study because they're not being tested?
That's right. That I do not know.
I'm thinking in the abacus of particular.
Yeah.
Are they using anything
Yes.
like an abacus system, un boulier en français, and would this serve as a symbol for them?
Yes, entirely possible. We've been talking to people on the ground there trying to understand how the math education works. Abacus hasn't come up yet. But yeah, we definitely need more insights, and also I agree with you, we need to look for alternative explanations that have to do with just sampling and noise and distribution of the data. It's definitely a next step. Yeah. And
so would your conclusion be then that non-symbolic representations do not play a causal role in development? You were quite cautious on that, right?
I mean, I think most of our data suggests that they don't, but that instead symbolic shapes those non-symbolic representations. So, but then the West African data lead me to pause again. So I don't know whether I can be entirely confident, but at least the conclusions from our Canadian data and then the recent stuff from Dan Hyde that I shared, I think are pretty conclusive when it comes to the developmental directions. And I think we also know, I mean, this is all correlational data, right? But we do also know from the training literature that at least the way that people have thus far tried to train non-symbolic number processing has not led to transfer to symbolic. Yeah. And rather worryingly as well, that training on non-symbolic doesn't even lead to very good near transfer to other non-symbolic tasks. So I think there's still a lot to do that we have to do in this space. But of course, the question is always, are we doing the training right? Are we doing the measurement right? Is that masking, is perhaps our experimental approach the wrong one? And do we need to revisit that? So I don't really feel in a position to give a fully confident answer. Right. But I think I personally find it a slightly more interesting question to consider how such a rudimentary system that has such clear evolutionary origins goes on to shape something that we transmit through culture, through education. Mm-hmm. And that process itself, I think, is where I want to focus my energies rather than on the question, is it or is it not?
Yeah, no, I appreciate your cautiousness here, because I think the metaphor of having 5 fingers it could be important. This could be a system that is so fundamental that it's present in many, many animal species. It's highly invariable, actually. Mm-hmm. And it does not easily change according to training on a purely non-symbolic manner, but that does not mean that it could not serve as a foundation. Mm-hmm. Some foundations could be so stable that they don't vary. So they actually don't submit themselves to the kind of analysis that you study here.
Absolutely.
And this leads me to another question, which is, would it be interesting to study extreme cases, perhaps of dyscalculia, where you actually lose this non-symbolic system? And maybe in this case, you would find that there is indeed a strong difficulty in the case in symbolic and formal mathematics.
Yeah. So you mean like at the single participant level, sort of a case study approach?
Like I'm reminded of these old studies of premature children that have right intraparietal anomalies and that are, as a consequence, have strong deficits in mathematics.
Yes. Yeah. I mean, we've looked at non-symbolic number processing and dyscalculics, and these were kids that we'd phenotyped very carefully over about 4 years to really show that they were stably low. And interestingly, we found something related to what you show in the paper with Manuela Piazza, was that the dyscalculic children, yes, they looked as though they were poorer on non-symbolic number comparison compared to matched controls who had no math impairment, but it was really only in the trials where number and area conflicted that they had great difficulties. So that made me sort of think that maybe their issue is more with focusing on number, and that it's actually, that is an indirect effect of their difficulty with symbolic number, because symbolic number hasn't really done as much of the sort of change and reorganization perhaps of the non-symbolic system. But that's just speculation. But it's interesting to ask, when children with dyscalculia show these basic number processing deficit, what is the origin? Is it representation? Is it the access to that representation? I think there, at least our data and some of Eric Wilke's data as well, suggest that it's more in the access to the representation rather than in the representation itself. But maybe again, like you say, that's possible, that it's possible that there is something about that representation that just isn't subject to individual differences. Yeah.
Super interesting. And so in general, the conclusion would be, regardless of the role of non-symbolic representations, that it's extremely, what drives the development, especially in the school age, is really the notion of a discrete number. Yeah. Starting with small numbers that are subitizable, 1, 2, 3, 4, maybe up to 4, and then the ability to attach symbols even to larger numbers based on that. So if that's my reading of your lecture, that this is really the key transition point. Yeah. We move to discrete numbers, leaving aside the idea of whether non-symbolic numbers is a foundation or not. This is the key moment is when you understand discrete numbers. Yeah. And so what sort of changes would you make to the curriculum or to the activities that children do in preschool or in first grade in order to foster that quicker? Do you have any studies on that?
I think sometimes perhaps in kindergarten, and I don't know what is going on in French school, so I'm just going by what I observed in Canada, is although play is wonderful and we must encourage play, the way that abstract academic concepts such as number and to some extent reading are introduced to kindergartners by offering them opportunities to construct that knowledge themselves. And I think what needs to change in kindergarten is that we need more intentional play with kids, where we orient them to number symbols, because we can't assume that they just pick them up by osmosis. Naturally, it's not going to happen. They need that direct instruction because they're being enculturated as such. So I think earlier attention to number symbols are more, one thing that I think is really positive is when children talk about numbers a lot, when they engage in discussions as a whole class. And then, of course, something that you've done a lot of research on, the use of number parts and number lines as instructional tools early on, which maybe not all educators are familiar with yet or have tried to use yet. I think those are powerful tools that can help us introduce children to number symbols early on. And I think as well that one thing that we've done that I hadn't had the time to talk about today is with younger kids in kindergarten, with several school boards, what we've done is test every incoming kindergartner for their knowledge of the cardinality principle. And what you will always find is that about, depending on the income level of the school board, about 80% of kids already have the cardinality principle coming in at age 4, but about 20% don't. And the teachers will find out eventually, but we can already tell them right there, this is the group of...
Explain what it's about.
Yeah, so the cardinality principle, the way we assess it, so the cardinality principle, the definition of it is that the last word in a count sequence represents the total number of items in a set. And the way we assess this is with a task that was developed by Karen Wynn, which is called the give-n task, where you essentially have a situation where you pretend that there's a puppet and the puppet likes to eat certain objects. Can you give the puppet X number of objects? And that's how we assess whether the child can relate the quantity that we are asking for to the process of exact enumeration, to giving out that number. And some young children will simply then grab all the objects in front of them, and as children develop, they initially become one knowers, so they're able to give one object when prompted, 2, 3, 4, and so forth, and eventually they become cardinality principle knower. And you can assess this in about 3 to 4 minutes, and it's such rich information that we found that educators really pick up on that. If they have this very clear distinction, you know, this child has this concept versus they're still developing it, they can differentiate the instruction earlier on. So that's one change that I like to see: simple assessment tools grounded in cognitive developmental research that make their way into classrooms to inform teachers in their ongoing work.
That's wonderful. I was just talking last week to Mathieu Lahaye, who was here on Wednesday night, also is a new director of a sub-direction of education in France. And Mathieu Lahaye was saying, whenever I visit a preschool, maternelle, I ask the child, give me 4. Give me 4 Legos. And that's exactly what you're saying. Yeah. It's a very good test of whether children understand something about, you know, even a number of size 4, size 5. And it's something that would be very easy to spread in preschool. In general, I think I take your message to be that we should introduce symbols as early as we can, basically, or more or less, or earlier than we think we should. The French education system is shy on symbols, also because we have this absurd, complex system with 70, 72, etc. So we always make fun of other countries, but this is really an absurd system. And so because of that, or perhaps for other reasons, we shy from going to the large numbers quickly. And I think that's a mistake. Maybe I'll turn that into a question to you as well, but do you know if there is any age limit, maybe in the sense of Piaget also, where you should not introduce symbols before a certain age because the kids are not ready? Or alternatively, is it just the case that the more you're exposed, the better you are, and you are in advance because you've been exposed to these concepts earlier?
I think the latter is more likely. I think this idea of certain stages, and anyway, I'm not, you know, chronological age, to me as a developmental psychology, is such a terrible metric for anything. You know, we use it, but it's meaningless essentially. And what we see, you know, in a city where I live, which is a city that's marked by a great gradient between the rich and the poor, like most of the world, unfortunately, is developing into that. But what you can really see is that some children from low-income areas, they don't develop the cardinality principle until they're nearly 6. So we've got this dramatic range, you know, and that's why I would never use age. I would always look at where is the child at cognitively. That's so much more important. So I think we can do it early. Of course, we need to respect that, you know, children learn through concrete objects into representations, into symbolic ones. We need to respect the developmental trajectory that they need to go through, but I don't think there's any reason why they can't start playing with the idea of symbols and thinking about relations between symbols and quantities quite early.
Right. Thank you. That's very much what I thought you would say, and I'm glad to hear it clearly. We can do it earlier. This may be the message in 4 words. We can do it earlier in preschool, in maternelle.
And then we need to sustain it, right?
Yeah. And we need to sustain it and ground it in concrete sets as well. Well, I think we can open it to many more questions. Maybe I come back to you, but I don't know. I know that there are experts in the room. There is Evelyn Egger, who is an expert of numerical cognition. Online, we have Véronique Izard as well, so don't hesitate to ask questions online as well. But we'll take a first question, monsieur.